So let us learn about vertical asymptotes. The vertical line x equals to a is called the vertical asymptote of the curve y equals to f of x if at least one of the following statements is true. Limit f of x as x approaches a is infinity, or limit f of x as x approaches a is negative infinity. Limit f of x as x approaches a from the left is infinity or negative infinity. Limit f of x as x approaches a from the right is infinity or negative infinity. So in order to determine if a line is a vertical asymptote, first of all, we need to determine all the potential vertical asymptotes. So for instance, we have this function y equals to 2x over x minus 3. To determine the potential vertical asymptotes, let's set the denominator to be 0. And then we will solve for x, we get x equals to 3. Now we would like to determine if x equals to 3 is an asymptote, particularly a vertical asymptote. So let's find the limit as x approaches 3 of 2x over x minus 3. For such a function, in order to find such a limit, we can always split the limit into the right side limit and from the left as well. Because it is enough for one of these limits to be infinity in order for us to have a vertical asymptote. So in fact, we do not need to find the overall limit. We can just find the right-sided limit or the left one, because if only one of them is infinity or negative infinity, this would be a vertical asymptote. Let's check the limit of 2x divided by x minus 3 as x approaches 3 from the right. So when x approaches 3 from the right, let's plug in to see what we get. So in the numerator, we have 3 times 2, this gives us 6. And in the denominator, we have 3 a bit larger than 3, so as we approach 3 from the right, minus 3. So if we have a value slightly larger than 3 minus 3, this is 0. It is 0, but it's a bit larger than 0, so we can write this as 0 from the right. So, in other words, limit of 2x divided by x minus 3 as x approaches 3 from the right, it's 6 divided by 0 from the right, and this is equal to positive infinity. We will write a property or a conclusion about this, about why 6 divided by 0 from the right is equal to or approaches infinity. However, as x approaches 3 from the left, again let's plug in, 3 times 2 is 6. A value slightly smaller than 3 but very close to it. So 3 minus 3, this is 0 from the left. 6 divided by 0, 6 divided by a value a bit smaller than 0, but very close to 0 gives us negative infinity. And here we can see we got in both cases infinities. One was positive, one was negative, which signifies that yes, we do have a vertical asymptote. Only one of these two limits would have been enough to prove that we have a vertical asymptote. Now, since we computed both of them, we might as well take a look at the potential graph of how this might look. This is the asymptote at x equals to 3. As we approach it from the right, we approach infinity, and as we approach it from the left, we approach negative infinity. And this is a potential graph. Now, before I do this example, I just wanted to write a remark here, or a note, that whenever we plug in and we get a constant over 0 plus, or 0 plus means a value slightly larger than 0 but very close to it, so whenever we get something like that when we plug in, then the limit approaches infinity. However, whenever we get a constant c divided by 0 minus, which is a value very close to 0 but slightly smaller than it, this is negative infinity as long as c is greater than 0. And this is how I solve these limits on the top here. So let's continue with a few more exercises. Let's find the limit as x approaches infinity of log base a of x. As we learned in previous videos about functions, I will graph log base a of x. As you might remember, this is how the graph looks when a is greater than 1. I graphed it in purple. And the graph looks a bit like this when 0 is less than a less than 1. Of course, these are just rough sketches. Now, as you might notice, as we approach infinity, so let's say when a is greater than 1, as I approach infinity and I keep on going, the value of log base a of x will also continue on growing and growing until it will keep on growing. Therefore, we can say that if a is greater than 1, the limit of log base a of x as x approaches infinity is in fact infinity. Now, let's look at the condition when 0 is less than a is less than 1. The limit of log base a of x as x approaches infinity. So let's look at it. So if we keep on going, it will keep on decreasing. So we write that this is equal to, the limit is equal to negative infinity. And just as a side note, always graph simple functions. Or basic functions. If you want to review for functions, check out the previous video about functions. But graphing can often help us or help you when finding limits. We will see why. Let's say I wanted to compute the limit of sine of x as x approaches, let's take it maybe as x approaches positive infinity, and then we will do negative infinity. Since we know the graph of sine of x, why not draw it? So as you might notice, it keeps on alternating between 1, negative 1. It keeps on alternating. It never stops alternating. Because of that, as x approaches infinity, there are different values, so the right and the left limit will not be equal. Therefore, the limit does not exist. The same thing happens if we are looking at x approaching negative infinity. It will keep on alternating. Therefore, the limit also does not exist. Now, let's look at cosine x with a very similar argument. The function also keeps on alternating between 1 and negative 1. So, the limits from both sides are not equal. So, the limit does not exist. That's why it's really useful to graph functions, because these graphs can help us a lot in determining limits. Now let's look at arctan of x. Again, let's graph arctan of x. You will get a graph that looks like this. We have an asymptote at pi over 2 and at negative pi over 2. And as we approach infinity, we can see that the graph will keep on approaching pi over 2 but will never touch it, but it gets really, really close to it. Therefore, as we approach infinity, positive infinity, so as x approaches positive infinity, the limit of arctan of x is pi over 2. Now, as x approaches negative infinity, the limit of arctan of x is negative pi over 2. Now let's learn about indeterminate forms. So usually when you compute a limit, if you plug in like as x approaches 0, if you plug in 0 and get an answer that's a real number, then this real number is the answer of the limit. However, what if you get something that's not a real number? Let's check the possible cases. We already discussed if you get infinity, then we say that the limit diverges. However, what if we get something that's not infinity? Let's check. So if we get 0 over 0, we already discussed this one. You can simplify by factoring, by rationalizing, or by combining fractions. This is one of the ones we already discussed. However, what if we get infinity over infinity, 0 times infinity, 0 to the power of 0, infinity minus infinity, infinity to the power of 0, or 1 to the power of infinity? What should we do in such cases? So now we will see some examples in order to help us solve limits with infinity minus infinity and infinity over infinity. Let's start these problems and learn from them. So, if we have limit of x squared minus 3x as x approaches infinity, what we do first of all, we always do this, we try to plug in to see what we get. So if we plug in infinity, we will get infinity squared minus 3 infinity. Again, infinity squared is infinity, and 3 times infinity is also infinity. So this is infinity minus infinity. So whenever we have infinity minus infinity, the rule is that you have to factor the largest common factor, or factor the largest power of x, if this is easier to understand. So in this case, we have x squared and we have 3x. X squared has a larger exponent, so I factor out x squared. I get 1 minus 3 over x. Just a reminder, x squared times 3 over x. This is 3x, that's why this works. Now that I factored out the largest term, let's look at what I have inside the limit. One thing to keep in mind that we earlier explained, that 3 over x, this is a constant over x, and since x approaches infinity, this is a constant over x. Since x approaches infinity, then c over x approaches 0. So 3 over x approaches 0. What we are left with is limit of x squared times 1 minus 0 as x goes to infinity. We can simplify 1 minus 0 is only 1. So we get limit of x squared as x approaches infinity. This gives us infinity squared, which is infinity. In this case, we write the limit diverges. Now let's move to another example, which we will treat in the same way. This is from the book, page 130. So we have this fraction. Let's try to plug in order to see what we get. So in the numerator, if I plug in 3 times infinity squared, I will get infinity minus, instead of x, we get infinity. I will write it here, so it's infinity minus 2. We can see from intuition that here it's infinity squared and we're also multiplying it by 3. Now infinity squared is infinity, but we can see with intuition that this grew faster than this other term. So we will have infinity in the numerator. In the denominator, we have infinity plus 1. You can write it's 5 infinity squared plus 4 infinity plus 1, which we keep on adding infinities to infinities. This gives us infinity. Now, just to point out, in case in the numerator you were not able to see that this is infinity, it is okay. You can proceed to solve. In case you wrote it as infinity minus infinity in the numerator divided by infinity, it is okay. But now this is a sign that you should factor out the largest term, or the largest power of x. So what happens? The largest one is x squared in the numerator and x squared in the denominator. So in the numerator, I get 3 minus x divided by x squared, which is 1 over x, minus 2 divided by x squared. In the denominator, I get 5 plus 4 x divided by x squared, which gives me 4 over x, plus 1 divided by x squared. Now we can simplify. We can cross out the x squared. This gives us limit of 3 minus 1 over x minus 2 over x squared divided by 5 plus 4 over x plus 1 over x squared. Now, we agreed earlier that the limit of a constant over infinity is 0. So, here we have a constant over infinity, we have another one here, and another one here, and another one here. So all of these approach 0. Therefore, we are left with limit x approaches infinity of 3 over 5, and the limit of a constant is the constant itself, and this is our answer. Now let's look at a couple more examples. What if we had an absolute value? So, again, as we agreed, whenever we can graph and the graph can help us, then why not graph? So this is the graph of absolute value of x. In this question, we are approaching infinity. And just to point out, as I pointed out earlier, that on this side of the graph, the line is y equals to x. On the other side, it's y equals to negative x. So as x approaches infinity, the graph we are actually dealing with is y equals to x. So the way to proceed is, instead of keeping the absolute value, we can write it as x. And again, we can always plug in if plugging can help us. So if we plug in the numerator, it's infinity plus 3 all squared times infinity divided by 2, infinity to the power of 4. Again, infinity squared is infinity, and if we multiply it by infinity, we're even making it larger, it is still infinity. And infinity to the power of 4 is still infinity, and even if we multiply it by 2, it is still infinity. So if we plug in, we get infinity over infinity. So in such a case, as we agreed, let's factor out the largest power of x. You can absolutely proceed by factoring out x squared immediately from this parentheses. Now I will expand it and show you the long way just to make sure that you are understanding it. So we learned earlier in another video about factoring that a plus b all squared is a squared plus 2ab plus b squared. So x plus 3 all squared is x squared plus 2 times 3 is 6x plus 3 squared, which is 9. Let's write this down. So we get x squared plus 6x plus 9 times x divided by 2x to the power of 4. Now, let's factor out the largest power of x from the parentheses. We take out the x squared. This leaves us with 1 plus 6x divided by x squared, which is 6 over x, plus 9 divided by x squared times x divided by 2x to the power of 4. We have x squared here and x. Using exponent laws, they have the same base, so we can add up the exponents. So this gives us x cubed times 1 plus 6 over x plus 9x squared divided by 2x to the power of 4. Now we can try to simplify. So we have x in the numerator and then x in the denominator. We can subtract the powers. We get x to the power of -1 because it's 3 minus 4 is -1, or we can write it in the denominator. In the numerator, we get 1 plus 6 over x plus 9 over x squared. We agreed before in the previous exercise that whenever we have a constant over infinity, this approaches 0. So we have a constant over infinity here, and we have another constant over infinity. So both of them approach 0. This leaves us with 1 over 2x. So again, we can, since this is a limit, we can factor out 1 over 2 because it is a constant. Using limit laws, we can take it outside the limit. This leaves us with the limit of 1 over x. So 1 is a constant. This is 1 over infinity because x is approaching infinity, so this approaches 0. So now our answer is 0. And if you would like to look at the graph, this is the graph of 1 over x, and as you can see, as we approach infinity, the graph 1 over x, it is approaching 0. Let's move on to a second example. So always factor out the largest term you can. In the numerator, this would be 4 to the x. So this leaves us with 2x divided by 4 to the x plus 1. In the denominator, we factor out 15 to the x. This leaves us with 5 to the x divided by 15 to the x plus 1. One thing we can do is we can write this as 2 separate fractions that we are multiplying. And now we can separate the limits using limit laws. So we get the limit as x approaches infinity of 4 divided by 15 all to the x times the limit as x approaches infinity. Now in here, look what we can do. Instead of 2 to the x divided by 4 to the x, we can write this as 2 divided by 4 all to the power of x, which is also equal to 1 over 2 all to the power of x. Now for the 5 to the x divided by 15 over x. We can write this as 5 divided by 15 all to the power of x, which is 1 divided by 3 all to the power of x. Now let's continue simplifying. So, maybe one thing we might want to check. 4 divided by 15, let's plug it on our calculator. This gives a value of approximately 0.27. Now, let's try multiplying it by let's try multiplying 0.27 times 0.27 times 0.27, and let's continue doing that because here we have to the power of x and x is approaching infinity. So basically we are multiplying 0.27 by itself for infinite times. We will keep on doing this. And since 0.27 is less than 0, if we keep on multiplying it by itself, it will become smaller and smaller and smaller and smaller until it hits something really close to 0. So this is regarding our first limit. Now regarding our second limit, the same thing happens because half is also less than 0. Half is 0.5. If I multiply 0.5 by 0.5, I get 0.25. I multiply it by 0.25 again, it's 0.125. I multiply it by 0.5 again, it's 0.0625. And you can notice it keeps on getting smaller and smaller as it approaches 0. So here we get 0 plus 1. Same thing happens with 1/3. It becomes 0 plus 1. So this gives us limit, 0 times limit, x approaches infinity of 1 over 1, which gives us 0 times 1, which is 0. And this is our answer. Now let's move on to the final topic for today, horizontal asymptotes. The line y equals to L is called the horizontal asymptote of the curve y equals to f of x if either limit f of x as x approaches infinity equals to L, or limit f of x as x approaches negative infinity equals to L. So, let's take an example to see how we do this. We have the function f of x equals to square root of 2x squared plus 1 divided by 3x minus 5. So, let's take the limit, as the definition says, limit x approaches infinity of f of x Now, what should we do in such a case? Let's first plug in to see what we get. In the numerator, 2x squared, so it's 2 times infinity squared plus 1, and then we square root it. Even if we square root infinity, it will still be infinity. So this is, in the numerator, we have infinity. And in the denominator, 3 times infinity minus 5, so it's also infinity. This is what happens if we plug in. Because of that, this limit, when we get infinity over infinity, this indeterminate form, we should factor out the largest power of x. So in the numerator, we can start by factoring inside the square root. We can factor x squared. This gives us 2 plus 1 over x squared. In the denominator, let's factor x. This gives us 3 minus 5 over x. Now, this is equal to, let's take the x squared out of the square root. Remember, when you take a number out of the square root, you get the absolute value. And you are left with 2 plus 1 over x squared inside the square root. And in the denominator, x times 3 minus 5 over x. Now again, a reminder that as we approach infinity, the function we are working with is y equals to x. So in the numerator we can write x times square root of 2 plus 1 over x squared divided by x times 3 minus 5 over x. And now we can simplify, we can cancel out the x from the numerator and the denominator. This leaves us with 2 plus 1 over x squared under the square root in the numerator and 3 minus 5 over x. Again, reminder that 1 over x, this is a constant over infinity, same for 5 over x. So both of these approach 0. So our limit is limit of 2, the square root of 2 divided by 3 as x approaches infinity, and this itself is a constant. The limit of the constant is a constant itself. So our answer is square root of 2 divided by 3. Therefore, we do have a horizontal asymptote at y equals to square root of 2 divided by 3. HA is for horizontal asymptote. Now, looking at the definition, let's also find limit f of x as x approaches negative infinity. Let's copy the function 2x squared plus 1 divided by 3x minus 5. Again, if we plug in negative infinity, we would get in the numerator negative infinity squared, so it's infinity, divided by in the denominator negative infinity times 3, so it stays negative infinity minus 5, it's negative infinity. So we would get infinity over negative infinity. Now, given that we got infinity over negative infinity, we can factor out the largest factor of x. So, same procedure as above, we get absolute value of x. It's the same steps at the start. So I just copied this from above. It's the same thing. After that, it differs because as we approach negative infinity, the function we are working for absolute value is y equals to negative x. So instead of the absolute value, I can write negative x times 2 plus 1 over x squared divided by x times 3 minus 5 over x. And now I can move the constant outside using limit laws. So this is the same limit that we found earlier up here. And this limit gave us square root of 2 over 3. So now we get negative square root of 2 over 3. So yes, we also have a horizontal asymptote at y equals to negative square root of 2 over 3.